The p-value is a very important term for hypothesis testing. It is the probability of obtaining a value of the test statistic that is at least as extreme as the observed value, under the assumption that the null hypothesis is true. For a left-tailed test, it is the probability of obtaining a test statistic that is less than or equal to the observed value of the test statistic, assuming the null hypothesis is true. For a right-tailed test, it is the probability of obtaining a test statistic that is greater than or equal to the observed value of the test statistic, assuming the null hypothesis is true. For a two-tailed test, it is the probability of obtaining a test statistic that is at least as large in magnitude as the test statistic. Once we calculate the p-value, we can use this to make a decision to reject or fail to reject the null hypothesis based on its relation to the given significance level, alpha. Let p represent the p-value. If p is less than or equal to alpha, then we reject the null hypothesis, and we can say that there is sufficient evidence at the given level of significance to conclude that the alternative hypothesis is true. If p is greater than alpha, then we fail to reject the null hypothesis, and we can say that there is insufficient evidence at the given level of significance to reject the claim made by the null hypothesis. Note that we're not saying the null hypothesis is true, we're just saying we don't have enough evidence to reject it. This is true regardless of whether our test is a left-tailed, right-tailed, or two-tailed test. If the p-value is less than or equal to alpha, reject the null hypothesis. If the p-value is greater than alpha, fail to reject the null hypothesis. In this example, we will look at a set of sample data and determine whether we should reject or fail to reject the null hypothesis. A bottle filling machine is supposed to fill bottles with 20.0 ounces of soda. The amount of soda in bottles filled by this machine is known to be normally distributed with a standard deviation of 0.4 ounces. Jared, a quality assurance worker, examines 15 randomly selected bottles and finds a mean fill of 19.7 ounces. At the 5% significance level, does he have enough evidence to claim that the machine is filling all bottles to an average of less than 20.0 ounces? Let's go through this problem. Our null hypothesis, H sub 0, is that the population mean mu is greater than or equal to 20.0. And our alternative hypothesis, H sub A, is that mu is less than 20.0. Our sample mean X bar equals 19.7. Our population standard deviation, sigma, equals 0.4. Our sample size, N, equals 15. From these values, we can calculate our test statistic, Z sub 0. We've already covered how the z-score is calculated, so we won't go through the calculation here, but we'll get a test statistic of z sub 0 approximately equals negative 2.90. Our alternative hypothesis is that mu is less than some value, so our test is a left-tailed test. This means that the p-value for our test is the probability of obtaining a test statistic that is less than or equal to our observed value. From a calculator or technology, or from a z-table, this gives us a p-value of approximately 0.0018. We're told to use a 5% significance level for this test, so writing this percentage as a decimal, we have alpha equals 0.05. We compare our p-value to our significance level. Our p-value of 0.0018 is less than our significance level of alpha equals 0.05. Since our p-value is less than alpha, we reject the null hypothesis. We can say that at the 5% significance level, there is sufficient evidence to conclude that the machine is filling all bottles to an average of less than 20.0 ounces.